Okay, now we're going to look at, stopping potential, and we're also going to look at tension and strings for charges. Okay, so let's say I've got positive test charges that are traveling in this direction. Or even let's say they're alpha particles. Remember, alpha particle is a helium nucleus. Okay, and those are positive 2 in charge. Okay, of course, atomic mass of 2, atomic number of 2. So let's say those charges are going in this direction. And they have a beginning velocity of some value. So essentially they've got kinetic energy, right? And they have some kind of velocity equal to v. Let's call it that. So the stopping potential, what we need to do is set that equal to the electric potential energy. So if these particles are traveling in this direction, and we're going to use metal plates, okay, to stop them, what I can think about is, of course, kinetic energy going this way. To stop them, we have to convert all the kinetic energy, okay, into elastic potential energy. I can do that by, having a variable voltage source. This is my positive, this is my negative part of my battery, so therefore this part here becomes positive, this part here becomes negative. So what's my minimum, stopping potential? And let's say the minimum just before they get to the plates here. Well, we know we can adjust the voltage and then get them to stop just before they reach there and record the voltage for that. Okay, well, once I do that, I know my electric potential energy is going to equal Q times that V. So whatever Q is present there, I'll just give that a small letter Q. That has to equal the electric potential energy, okay, as it gets there. So what's my equation going to be then? So I'll have 1/2 mv squared, m being the mass of the particle, v being the velocity this time. I'll put a little vector head on that. Okay, that's going to have to equal Q times E times D. Because remember, volts is equal to E times D, right? Okay, so I can do that, or I can set 1/2 mv squared equal to QV. And this time V is volts. Okay, so if I'm recording my volts here, whatever volts it takes to allow those protons or whatever you've got, whatever charge, to stop just before that, that V recorded is going to be equal to stopping potential. I'll record that here. So if I have a variable voltage source, and that voltage source has a dial recording my voltage right there, then whatever volts on that, when these things come to a complete stop, that'll be called my stopping potential. But you can solve it theoretically too. If I have 1/2 mv squared, just divide by the charge, and I'll get my stopping potential that way. Okay, now what about, let's say I've got a positive charge here traveling towards a much larger positive charge here. Let's give this a capital Q, and this one here a little q. And I want to know what my stopping distance is. So how close can this particle here get to the center of this? And remember, we are measuring the radius from the center of the charge, okay, to the center of the charge there. So let's call that R. So how close can these two get to each other? Well, again, kinetic energy has to be converted into electric potential energy. Now this is a point charge. These are spherical charges, in other words, so we don't have a constant electric field at all. So this thing assumes has some velocity, and I'll put V with a vector head on it. What's the minimum distance these two centers can get towards each other? Well, I'm going to set the equal to, I'll say 1/2 mv squared, and I'll put a vector head on that so you don't get too confused, is equal to electric potential energy here. Okay, so then I will say that'll be then K, little q, big Q, divided by R. Now, where does this equation come from? Well, we know that electric potential energy of a point charge is equal to Q times V, right? Well, V is K, big Q, divided by R. So electric potential energy then associated with spherical charges, I'll just multiply this by the little q then, So we get kq little q divided by r, and k being our 9, okay, times 10 to the 9th. So then we can solve for r. R would be the minimum distance these two, okay, can get to each other. Now what if I just wanted to know the stopping potential for this? Well, then I'll just set kinetic energy equal to little q times v. So I'll have 1/2 mv squared of this particle equals the charge of this particle multiplied by v, and then solve for v. So v would then equal 1/2 mv squared, that's the velocity, divided by the little charge's value. So it'd be 1/2 mv squared of this divided by the charge of that particle, and that would be the stopping potential. And where would that occur at? It will occur at the closest distance that these two can get towards each other. Okay, and the last idea, what if I have two charges? I'll just label them both as Q, and they're both positive. It doesn't matter, they could both be negative. Okay, how could I find the value of those two charges? Let's say they are both mass m. Okay, I want to figure out their charges. Well, a very similar system that we've seen before. Okay, we have force gravity downwards here. Okay, and I'll change colors here to help us see it above here. Okay, so we then have force up this direction. We have a force in this direction and a force in this direction here too. I'll draw that just a little bit longer to make it easier for you to see. Okay, going across like this. I'll draw that a little bit longer again. Okay, there you go. The force in this direction here is going to be force tension Y. This one here is force tension X. Okay, and let's draw a line going through here like this, down the center. We'll have an angle theta here, and then there's another angle theta right here. Okay, so it'll be force tension X acting on this sphere must equal the force electric, okay, going in this direction here. Well, looking at this angle here, this angle equals this angle here, and we can use the tangent function. The tangent of theta is equal to opposite over adjacent, so I'll say tangent of theta, okay, is equal to the opposite force tension X divided by force tension Y. Okay, and what's force tension Y equal to? Well, it must equal force of gravity going downwards here. So we have force gravity downwards, force tension Y upwards. So we know that force tension Y is equal to mass times gravity. So force tension X, if we solve for this expression, must equal mg tangent of theta. Okay, so then force electric equals force tension X. Therefore, mg tangent theta has to equal k q times q divided by r squared, because their q's are both the same values here. Okay, now you'll use a little bit of trigonometry. You must get the distance between these two here. That would be the radius r here that we're talking about right here. Well, if you know the length of the string here, the length times the sine of theta will give you this part of the triangle here. Okay, double that to get the total distance there. So I'll write there r is going to equal 2 times the length of the string times the sine of theta. And that's how you deal with tension forces, okay, with charges that are opposing each other. And then mg tangent theta will be known, r squared will be known, k is our k constant, to solve for q.